Okay, let me see. Okay. Okay, good afternoon, everybody. Today I'm going to talk about the quantum theory of light. I feel that this is a rather difficult subject and also challenging. So perhaps it's good for us to leave it to the end of the course and talk about it. Because I view this course as a lifelong learning project that you will keep learning about this subject even after you have left this course. So I presume that quantum theory of light is one of those subjects that are quite difficult to understand, but it is interdisciplinary. So perhaps you will enjoy learning about this subject. So this is the outline for lecture 38 that I took from last year's lecture notes. Okay, I'm going to modify this a little bit for this year. So the first thing I like to mention is that light is a wave, and that has been known for millennium. Not millennium, but perhaps for hundreds of years. Okay, this is Newton ring experiment. This was done about 1717. Okay, and Newton showed that if you have two light waves, like if you have an object and if you focus it so that it get reflected off the lens, and if there is an interference pattern that you can see from this thing, and you can see that there are interference pattern due to the different path length of the light, forming what is called a Newton's ring. And that was a clear signal that light is a wave. And of course, the other one that is very famous is called the double slit experiment. And this was first done by Young in around 1801. So it's been known for quite a while that light behaves like a wave. But then even at that time, during Newton's time, it was thought that light was a particle, but then those theory did not hold up very well. And the viewpoint that light was a particle was abandoned until recently when we talk about Planck's radiation law. Okay, so what we found here is that if you were to look at the cavity, and if this cavity is heated to a temperature T, and then if you dig a small hole in the cavity and look inside, okay, you will see radiation from the cavity hole. And the usual theory is that there are electromagnetic modes inside this cavity. And it corresponds to a wave bouncing around, and some of those waves would leave this cavity through the hole, and you will see the spectrum. And the spectrum of the cavity is actually quite interesting. And this is called black body radiation. So if you were to look at the intensity of the light that comes out of the hole, okay, the intensity that comes out of the hole, and that's a function of frequency, there's very little radiation when the frequency is low, but as the frequency increases, the radiation increases. But if you heat the cavity up with increasing temperature, you see more and more radiation, okay? And what was found was that as the frequency goes up, the radiation peaks and then it peters out and comes down. Okay, it peaks and it comes down. It peaks and it comes down. And nobody knows why. Why does it peak? Until Planck came about, Max Planck, proposed that photons are quantized, electromagnetic energy is quantized, and they're quantized according to the frequency of the mode. Okay, photons are quantized. And each photon, this corresponds to energy of a photon. So instead of having continuum of electromagnetic modes bouncing around, you have photons bouncing around, and those photons can each carry a packet of energy. Okay, this is a packet of energy. And then what we have is that the Planck constant is very small. Planck constant is on the order of 10 to the minus 6 times 10 to the minus 34 kind of thing. So it's a very small constant. So this packet of energy is very, very small. And hence the higher the frequency, the higher this packet of energy. And hence optical photons are easy to observe. And then microwave photons are more difficult to see, to observe, okay? And Planck actually fitted this data to a very nice theory that the energy of the electromagnetic modes are quantized, and it could fit the experimental data quite well. But he doesn't know why, okay? It's just an indication that the electromagnetic energy of a photon is quantized. Another experiment that shows that electromagnetic energy is quantized is the photoelectric effect. And what they show is that if you were to shine light onto a surface, a metal surface, then electrons will get kicked off the surface, and the electron that get kicked off the surface is proportional to h bar omega, and only when h bar omega reaches a certain value that is able to kick the electron off the orbit of electron, as you know, are particles orbiting around a nucleus, and if you are able to apply energy enough, then you can kick the electron off the orbit, and the electron will become free, and it becomes freely moving. And they found that this energy is actually proportional to h bar omega, and it comes in packet. It doesn't come continuously. Okay, it comes in packet, and hence this was another indication that the energy of a photon is quantized. Okay, so then people came up with this wave particle duality concept later on. And a particle can be both a wave and a particle. Okay, a particle has a momentum that is associated with its mass, okay, but it's also associated with the wavelength of the wave. So a wave is associated with a particle and de Broglie postulated that the momentum of an electron is proportional to the wavelength of the wave. So the shorter the wavelength, the larger k is, then the higher the momentum. And this is observed in the electron, actually first observed in the electron. And then it's assumed that a photon should also have such a property that it has a momentum. And if the wavelength is very short, then the momentum is quite high. Okay, so what we want to do then is to actually study the particle in the quantum world. Okay, particle in the quantum world. Before we do that, when we like to study a particle in the classical world. To do that, we assume that the particle is that of a very simple pendulum. It has a mass attached to a spring X. Okay, and then we know that the potential energy, according to Hooke's law, potential energy according to Hooke's law is half kappa x squared. Okay, this is just Hooke's law. Okay, and we know that this particle would oscillate, that if you were to let it be freely running, you find that X oscillates. Okay, that we know from classical theory. And we like to connect this pendulum in many different ways, but we also would like to use Hamiltonian mechanics to study this pendulum. Actually, we had a precursor to this before, because when we were studying the Drude-Lorentz Sommerfeld model, we came across the case of an electron bound to an atom with a charge, and then we say that the simple model we have is to invoke Newton's law, that mass times acceleration is minus the spring constant times x. Okay, this is just Newton's law. And this is called the equation of motion. For this simple pendulum, and we also saw that in the case of the Drude-Lorentz Sommerfeld model. And we like to equate this thing using Hamiltonian mechanics as well. Okay, how do we do that? It turns out that in terms of Hamiltonian mechanics, we have to first find the Hamiltonian of the system. The Hamiltonian of the system is the total energy of the system. It is given by the kinetic energy plus the potential energy. And we found that the kinetic energy, which is also T, is actually equal to half mv squared. Okay, but we can write it more suggestively by writing it as 1/2 m squared v squared, and call this p squared. So it can also be written as p squared over 2m. That is the kinetic energy of the pendulum. If you have this pendulum and if it's attached to this with a spring, and if it does move, okay, with the velocity, that is the kinetic energy. And as we say, the potential energy, which we also call V, is by Hooke's law, half kappa x squared. Okay, so the total energy of the system then is equal to T plus V is P squared over 2m plus half kappa x squared. Okay, it turns out that you can also derive the equations of motion from this Hamiltonian by requiring that the Hamiltonian as a function of time has to be 0 for energy conservation. Okay, so this Hamiltonian, as you can see, is a function of the momentum and the position x. Okay, and if both the position and the momentum are functions of time, the momentum and the position is a function of time, they have to move in tandem so that h is kept a constant. So what we have then is that if this is true, then the h dt by partial derivative is the same as the h dp dt plus the h dx dt. Okay, so p and x are called conjugate variables in physics. And they have to vary in tandem so as to make h a constant. So if h is a constant, then this must be 0. So in order for this to be 0, there are many ways that it could be 0. One way for it to be 0 is to have to have dx dt equal to dh dp. And then you can have dp dt equal to minus dh dx. Okay, you can look at this equation. One way for it to be 0 is to have these two things being varying in this manner. If dx dt is chosen to be dh dp equal to this, and then dp dt is chosen to be negative of this, then this would be 0. And then you can use this Hamiltonian that we have written down, which is this one over here. If you use the fact that the Hamiltonian is given by p squared plus 2m over half kappa x squared, and using this equation, these are also called the Hamilton equation. Okay, you can show that the x dt is p over m, and then the p dt is equal to minus kappa x. Okay, you can show that quite easily because when you differentiate h with respect to x, then you put the minus sign in front of it, you get this minus kappa x. If you differentiate h with respect to p, you get p over m. And if you combine these two equations, then what you have is that the p dt is just m d square x dt square is equal to minus kappa x. So this equation of motion is not derived using Newton's law. It was derived using conservation of energy and Hamilton equation. So previously we say that if you were to apply Newton's law, like over here, that as we did in the Lorentz-Sommerfeld model, okay, we derive these equations of motion. But one need not have to do that. One actually can start with the total energy of the system requiring that the two variables p and x, which are called the conjugate variables, vary in tandem such that the Hamiltonian is kept independent of time. And if that is kept independent of time, you can derive the same equations of motion, okay? And you can solve these equations of motion quite easily. You will find that in the textbook, this kappa x is often written as minus m omega naught square x, okay? Where omega naught square is the resonant frequency of the pendulum. So if you have a pendulum attached to a mass m, you can easily show that the resonant frequency of this pendulum is kappa over m. Okay, if you take omega naught square times m, it would just be kappa. Okay, so you can solve this equation very easily. And if you solve this equation, if you substitute this back in here, you have d square x dt square is equal to minus omega naught square x. And then you would have just a solution that x is equal to a sine of omega naught t. It's a second order equation, so you should have two solutions. Okay, or you can write it as one with a phase. You can also write it this way. There will be two independent solutions. So the reason why I want to use Hamilton mechanics or Hamilton mechanics to describe this instead of Newton's law is because Hamiltonian mechanics is what motivated quantum mechanics. Okay, let's see how Hamiltonian mechanics motivated quantum mechanics. So H is equal to kinetic energy plus potential energy. This is KE, this is PE, okay? And then it is often written as kinetic energy is equal to P squared over 2m. And then the kinetic energy term motivated by de Broglie's result. This is from de Broglie's law. Then we can actually write the Hamiltonian as the kinetic energy being h squared k squared over 2m. And then the potential energy is half m omega naught square x. Okay, this is the potential energy part. And then this is the total energy of the system. And then at that time, Schrodinger made the observation that energy of the system is related to energy of the photon, and let's call that h bar omega. Okay, h bar omega. And then how do we derive Schrodinger equation from this? Okay, how did Schrodinger got the light bulb for Schrodinger equation? Well, if you look at this equation, he says that if this equation is going to be operating on a wave function instead, okay, if this equation is going to be operating on a wave function, and then it will be something like h bar omega psi t. Let's assume that the wave function is very simple. The wave function is just a plane wave, like maybe a constant times e to the minus I omega naught t. Okay, let me see, just, sorry. This is just omega, okay? Notice that this is not omega naught, okay? This is omega, this is not omega. The two omegas are different. This omega naught is the resonance frequency of the pendulum. Omega is just a unit for energy over here. And then let's assume that it's just looking like a plane wave. So in the space dimension is varying like that. Let's assume that is multiplied by a function a naught. A naught is the slowly varying function of x and t. Okay, this is slowly varying function of x and t. And in the limit, when this is not changing with x and t, then I know that k squared psi xt, okay, k squared psi xt can be replaced by partial square, partial x squared psi xt. If psi xt is something of this form, then k squared psi xt is something of that form, okay? And then if psi xt is something of this form, and this is very slowly varying, then h bar omega, or omega, I can say omega psi xt, okay, is roughly equal to partial t I psi xt. Can you see that? Okay. If I assume that the envelope is slowly varying, okay, this part is slowly varying, and if you were to substitute these equations back there, I would see that my k squared is similar to partial square, partial x squared. My omega is similar to first derivative in time. And then I can convert this equation into a partial differential equation. Okay, if I do that, then what I have then is that I have something like h bar square over 2m, which is something coming from this first term. Okay, this term times this term. And then I replace the k square with minus partial square, partial x square. Okay, and then this term multiplied by psi xt, I just plug it in like this. Okay, and then the second term, I leave it the way it is. It will be half m omega naught square psi xt. And then the right-hand side is h bar omega, but let me replace it with a time derivative. Okay, so this equation is deeply motivated by Hamiltonian mechanics, and it's deeply motivated by de Broglie's finding that h bar k is the momentum of the particle, and then it's also deeply motivated by the photoelectric effect and Planck's observation that the energy of a photon is h bar omega. And H is the total energy of the system, and let me call this h bar omega. And having done that, I convert this into an algebraic equation such as this. Furthermore, I can convert this equation into a partial differential equation. Okay, and voila, we have Schrodinger equation. Okay, so this is Schrodinger equation in this simplest form. As you can see, it's motivated by many findings of that time. And you probably have observed that, if I do a paraxial wave approximation, in the paraxial wave approximation that we studied when we studied the Gaussian beam, we look at this expression. We said a wave can be thought of as an envelope function times a rapidly varying function. And as the frequency gets high, and as k gets large, which means that the momentum becomes large, this part is very rapidly oscillating and varying, and this part is slowly varying. And if you were to take this second derivative of this function, only this term would dominate. I think we did the analysis of that for paraxial wave approximation. And also, if this is slowly varying with time, with respect to time, and if you take the time derivative of the whole thing, then this one will just become this one over here. So you can think of Schrodinger equation being this. However, if you were to make the paraxial wave approximation on this term, and then if you were to make the slowly time varying approximation on this term, you get back this algebraic equation, which is essentially just the equation from the Hamilton. The Hamiltonian of the system is equal to that. Okay, so the two are connected in this manner. Okay, so this Schrodinger equation can be solved by the separation of variables. It's a PDE. You can use separation of variables to solve this, or you can convert this into a series of eigenvalue problems. So what you do then is to actually assume that Vxt by the separation of variable might be written as Vnx. And the other function, you can actually see that it is writable in this fashion. Okay, this is actually the standard procedure for separation of variables. And then when you plug that back in, you convert the above into an eigenvalue problem. It will become just partial square, partial x square, psi of nx plus half m naught omega naught square x square psi of nx is equal to, and if you differentiate this with respect to t, you bring down an omega n, and if you call that E sub n, okay, E sub n is h bar omega n, then you convert this into an eigenvalue problem. En is the eigenvalue, and psi nx is the eigenfunction. Just like what we have done for waveguide problems and cavity problem, eigenfunction or eigenvector. Okay. And so what they like to do in the physics community is actually to write this using direct notation. You call this the whole thing. Okay, the whole thing can be written as minus h squared over 2m partial square partial x squared plus half m naught omega naught square x squared psi sub nx is equal to En sine nx. And this can be thought of as an operator. And in quantum theory, an operator is usually denoted with a hat. And then this is a vector. In direct notation, the vector is usually denoted by something called a cat notation. Okay. And then in terms of direct notation, this eigenvalue problem can be written in this manner. And this notation is entirely analogous to the matrix notation, that this is just a matrix operator operating on the vector psi, which is equal to the eigenvalue E sub n times psi. Okay, we can call this psi sub n if you want to. Okay, we can call this eigenvector psi sub n if you want to. Okay, are there any questions so far? So what we have done here is to show that Schrodinger equation is derivable from Hamiltonian mechanics or motivated by Hamiltonian mechanics. It's actually postulated. It can never be derived. Okay, it's postulated by Schrodinger. And because of his postulates, the equation can predict a lot of the energy levels or the eigenvalues of a hydrogen atom. You can write this in the equation in 3 dimensions, and this becomes like a 3D cavity problem. This is like a 1D waveguide problem or 1D cavity problem. But if you write this in 3 dimensions, this becomes like a cavity problem. And then the cavity has resonant frequency. Those are called the eigenvalues. And Schrodinger found that the eigenvalues found using his equation agree very well with experimental finding of that time. So his equation becomes something of a great success during his time. But he doesn't actually understand what these equations mean. Okay, that was the interesting part. Okay, so why are we interested in this? Well, what I'm going to say is that when you have a pendulum can be described classically in this manner, but it can also be described quantum mechanically with Schrodinger equation, okay, or Schrodinger equation in this manner. And then when it's described by Schrodinger equation, the pendulum is described by a wave function instead of a position. So what happens is that if I were to compare the case of a pendulum, then it is denoted by a position x. But then in the quantum world, okay, the pendulum is not denoted by a function of a particle like this, but is denoted by a wave function psi of x of t. Is what Schrodinger equation says. Okay, so what happens is that in Schrodinger equation, the pendulum is not denoted by a, let me see, what do I have? In Schrodinger equation, over here I have it. the pendulum is not denoted by a function x alone, a position x alone, but described by a wave function. The wave function has to satisfy this equation, okay? So what this wave function does is that it says that the position of the is fuzzy in its location. You do not know actually where it is, okay? That's why you describe it with a wave function. So if you have a classical oscillation on the left-hand side, okay, and then if you have a particle that is quantum, it actually is fuzzy. You don't know actually where it is, and its position is not deterministic. And if you were to plot the same function as a function of time, you will see that its amplitude is actually fuzzy. Okay. So the wave function is actually used to describe the fuzziness of the location of the particle. Okay. So this has gone through quite a bit of trouble for the quantum physicists because they do not actually understand what this wave function meant. It was actually Max Born who say that if you find a wave function psi of x of t, it is the square of this that is proportional to the probability density function for finding the particle at x and t, okay? So because this is a probability density function, it is required that if you were to integrate this thing over the location of the thing, this has to be 1 because it's a probability density function, okay? So are there any questions so far?
Professor Chu, I have a question about the localization of the particle when we derive the Schrodinger equation. Is this the average, some average of the positions in time?
The particle is not fixed in its location in the quantum world. The particle is fuzzy, it can be anywhere, everywhere. Okay, so because the particle is not fixed in its location now, there's a way of describing its position. You can only describe its position in the average sense. Okay, since that size of xt square is the probability density function, the average location of the particle, okay, let me denote an average with this, would be described by this function. As you learn in probability theory, if this is a PDF, if this is a probability density function, to find the average of a random variable, you do this. And x is a random variable now. X is a random variable. And this is also a random variable. Okay, so x is not deterministic anymore, but random. And in order to give this random variable is random property, you have to have a way of describing its mean and its variance. Okay, you have to have a way of describing its means and its variance, and then you can show that, let me see. Let me see. So it's a random variable. I thought I have the formula for the variance written down somewhere. Apparently, I didn't have it written down. Maybe it's over here that I wrote it down. So you can also describe this variance, and then you can actually say that the variance is given to be the average of the square of the random variable times the or minus the square of the average. Okay, this is the variance of the random variable. So this is a random variable. You can find this expectation value. This is called expectation value or the average. Okay, so this is called the average, which is also this value, and it will be defined by this integral. Okay, and then of course you can also find the this will be given by this thing over here. And from this, you can calculate the variance. So because of this formula, you can find the expectation value. This is called the expectation value. Or just simply average. Okay, using this wave function. So the wave function that comes with this problem now, endow the particle with a lot more properties. It has a mean and it has a variance. And the position of the particle is random, which means that if I were to look at this particle, okay, let me see. So if I fix t and just plot this psi as a function of x, it can be complex value, but let me just plot the real part of this. This function, which can be a solution to this wave equation, which is this Schrodinger equation. Okay, this equation I have over here can be a complex value function. Okay, and then associated with this function is the concept of probability, which means that if I were to square this function, I may get something like this. Okay, always positive or something. This is a probability density function. So because of the fact that you need to describe a particle not just with a position, but a wave function, you endow the particle with a lot more information that it ordinarily has. Okay, in the classical mechanics, a particle is only described by its position and its velocity. Whereas in quantum mechanics, the particle has a position, which is its mean value part plus a standard deviation. And also what happens is that in classical mechanics, in order to describe this particle in classical mechanics, for instance, if you know its position and its momentum, you can predict where this position and momentum will be in the next time using finite difference method, because I can always solve this equation by using finite difference time domain method and keep track of the position and the momentum of the particle. But in quantum theory, that is not enough. You need to keep track of the whole wave function. Okay, you need to solve the whole PDE. And what is more important is that the momentum actually, the momentum is actually been described by a derivative operator. Remember, this part of the operator, this part of the equation corresponds to the momentum of the particle. The momentum of the particle is not described by just a simple function, but the derivative of the wave function. Okay, so one of the things that you learn is that P with h bar k, and in the quantum world, this becomes partial x psi x t. Okay, so this actually becomes a momentum, and we call it an operator now. We call it p hat, and this is called a momentum operator. So you see two important changes here. The position of the particle is not described by x alone, but by a wave function. In order to find its position, you have to take expectation value or average value. The momentum of the particle is not given by h bar k, but given by this thing operated on the wave function. And you can see that in the limit, when this becomes a plane wave, okay, this operator just becomes the classical operator or classical description of the momentum. So we call this the momentum operator because it is now a derivative operator. Okay. So what we like to connect to is the fact that if you have an electromagnetic oscillation in a cavity, you have modes, okay? And if you just look at the fundamental mode of this cavity, this mode is going to go up and down. And if you were to fix your eye on just one position of the oscillation, this thing is going to look like a pendulum. Okay, so this is going to oscillate like a classical pendulum. But in the quantum world, we have to replace this classical pendulum with a quantum pendulum, in the sense that the classical description of a pendulum is not enough. We have to replace it with a quantum pendulum and describe that quantum pendulum with a Schrodinger wave equation. Okay, so this mode, this particular mode, will oscillate back and forth, and it looks like a simple pendulum. And in quantum theory of light, what we need to do then is to replace this classical pendulum, okay, to become a quantum pendulum. So we have to understand the quantization of a simple pendulum in order to understand the quantization of light, okay? So what we have is that you can actually think of Maxwell's equations as being the equations accounting for the coupling of oscillators. You can see that when we have a series of harmonic oscillator, like if we have a simple Planck circuit, it oscillates. If we have two of them, we will have two resonant frequencies. If there are three of them, we will have three resonant frequencies. But if you have many, many of them, we will have infinitely many possible resonant frequencies. And for instance, you learn in transmission line theory that the transmission line can be thought of as a coupling of infinitely many LC tank circuit, and hence, if you solve for the resonant modes of the transmission line, it has infinitely many modes. Okay, you can think of a wave propagating through space as due to the coupling of harmonic oscillators or pendulum, and you can think of Maxwell's equations as being due to the coupling of harmonic oscillators in a 3D space. Here, I just show you a 2D picture first. Okay, so at the basic level, you can think of space as being consisting of electron positron pair. Okay, a positron is an antimatter. Okay, so if you have the electron together with the positron together, they actually amount to no mass because one has the negative mass, the other one has the positive mass. And together they are lurking in vacuum. The electron-positron pairs are lurking in vacuum. And together in the quiescent state, they amount to nothingness. They amount to nothingness. So when you have an electromagnetic wave that propagates through vacuum, you're essentially polarizing this electron-positron pairs. Okay, giving rise to coupling of harmonic oscillators next to each other. And then that gives rise to wave propagation. That's why electromagnetic wave can propagate in vacuum for that reason, because of the EP pair. And then, of course, you can think of Maxwell's equations is nothing but the description of the coupling of this EP pair. And then D is epsilon naught E plus P. But then if there's no matter, we just have this one. But even this one will support a wave. So even if we have no matter, no material in space, just vacuum by itself, the fact that this part is polarizable will contribute to displacement current, and it gives rise to displacement current that couples to Faraday's law, and that gives rise to wave motion that can propagate through space. Okay, so what we can think about is that electromagnetic oscillation is actually due to the polarization of EP pairs, and each of these EP pairs can have a quantum effect. They can be thought of as a quantum harmonic oscillator in addition to being a simple harmonic oscillator. So if you look at a simple pendulum, okay, here is the description of a pendulum in a classical way. But if you were to describe this pendulum, this particle with a wave motion, you can have different kinds of modes. Okay, these are different eigenmodes of that Schrodinger equation. And you have different eigenfunctions, and each of these eigenfunctions will look something like this, and there are many, many of them, infinitely many of them. So if you look at this eigenmodes of this equation, which is what I was alluding to, okay, you can take Schrodinger equation. Let me see, let me make this small. Take Schrodinger equation, convert it into an eigenvalue problem, and look for all these eigenmodes. Okay, again, solve for these eigenmodes using known knowledge in partial differential equations. You can find all these eigenmodes, and these eigenmodes have been plotted, and those are eigenmodes with different energy value. E sub n, you can solve this equation in closed form. Okay, you can solve this in closed form, which is what I'm saying here. Okay, you can solve this in equation in closed form. You can find that En is n plus half h bar omega. No, okay. You can find that that is what your En is, and then And then this is just a plot from Wikipedia as to what those modes are. Okay. And then they have different different eigenvalues. In the momentum actually has been described by a partial differential equation operator. And then the strange thing about this eigenmodes is that there is one mode here. There's this one mode here which corresponds to n equal to 0. N is equivalent to the number of photons that you can have in this oscillating modes. And n precisely, each of them has an energy of h bar omega. Okay. So this actually should be corresponding to omega naught of my lecture note. Okay. And this mode here corresponds to 0n. This mode is called a 0-point energy mode, E sub 0. Okay, this is the lowest mode, which is the ground state mode. You can find that it has 0 mean in terms of position, but its energy is not 0. Okay, its energy is not 0 because if you set n is equal to 0, it's still an energy value associated with this mode, and that is called the 0-point energy. And this is something only predictable by quantum theory of light. Okay.
I have a question.
Yeah, sure.
What will happen with the eigenstates of energy, eigenvalues of energy if the potential well will have different shapes, say x to the power 4 or something like that?
Oh, then it's not a simple harmonic oscillator anymore. The case that we consider here is a very simple one, where this potential well is very simple. And as I said before, you're considering the case where this part is quadratic. It's proportional to x squared. It can be x cubed or x fourth or some very, very strange value. Then this equation has no closed form solution. Most of the time, it does not have a closed form solution. But if it is x squared, it can be solved in closed form. I will describe that in the lecture note. It's been solved using the knowledge of ordinary differential equation from the 1800s. Okay, in terms of Hermite Gaussian polynomials. So you can use some very old knowledge to solve those equations, and it will give you these wave functions. Okay, so what is important is that when you translate this to describing the pendulum, in a classical pendulum, it says that the amplitude of this oscillation is very deterministic. Okay, it's very deterministic. You can follow its oscillation quite easily. Okay, but if this is quantum, it says that the position of this pendulum, if I think of this as being equivalent to a pendulum, the position of this pendulum is not deterministic. It's actually is something that is fuzzy. Okay, and I can think of a quantum pendulum as a case where the position of the particle is not deterministic. And this is found in experiment as well, in the sense that if I were to, say, measure light to very high precision in a laboratory, I find that the electric field can never be measured precisely. It has always a kind of randomness involved. Here you can see that this is the mean value of the electric field if you were to do measurements over and over again. And these are the variance of the electric fields. And if you were to do an experiment, you might end up by having one of these dots in the experimental data. So quantum theory of light says that the amplitude of light is probabilistic because you connect the amplitude of light to the amplitude of the pendulum. The amplitude of the pendulum is deterministic in the classical world, but in the quantum world, as you can see, the amplitude is random. Okay, the amplitude can be anywhere in this picture over here. So, are there any questions so far? So just bear in mind, replace the classical pendulum with a quantum pendulum, then amplitude of that pendulum is random. Okay.
Amplitude is random, but the average value is still following the classical laws, right?
Yeah, the average value is supposed to follow the classical value. But these are the solutions that they have found in the very beginning, which is that when they solved Schrodinger equation for the pendulum, okay, they found these solutions, which are the eigensolutions of the equations, and these are called the photon number states. The bizarre thing about this photon number states is that if you were to take the average, if you look at these functions, okay, I want you to remember these functions. They're either odd functions or even functions, odd functions or even functions, okay? And if these wave functions are supposed to describe the position of the particle, okay, and what you have is that you have a bizarre nature. Let me see. That the average value of the position, according to the probabilistic interpretation of quantum theory, you're supposed to calculate the average position that way. And of course, phi nxt for a particular mode is equal to phi nx e to the minus I omega nt, okay, for that particular mode that you have found. So this is essentially just the x psi n x squared. Okay, notice that this function is always odd because I put this x on the outside. And notice that size of n is either even or odd, but when you square them, they always become an even function. Okay, can you see that? If you take this function and square it, it becomes an even function. So if you were to evaluate this function, it's always equal to 0. Okay, for all. And these are called the photon number states. They're called photon number states because the energy is n plus half h bar omega. And each of them has energy level that is, if you add h bar omega to each of this energy level, you get the next energy level, okay? So they are precisely having the energy levels of photons. If you look at the spacing of this energy level, they're precisely that of a single photon, okay? That's why they're called the photon number states. But the unfortunate thing about them is that the expectation value of the position of the particle according to this photon number state is always 0. So hence we call this state non-classical state. Non-classical states because a pendulum is not behaving like that. We know that if the pendulum oscillates, okay, it has a average position and average momentum that is not 0. Okay, so how do we do that? So the answer to this is actually in finding the coherent state. Okay, here is actually lecture 39 onward. Okay, the coherent state will find the solution to this problem, the answer to this problem, because for a long time, quantum physicists were puzzled by the fact that why do all those photon number states give rise to 0 average position? And if you look for the momentum as well, if you differentiate this function, okay, if you differentiate an odd function, it becomes even. If you differentiate an even function, it becomes odd function. And if you use the same interpretation to find the probability of the momentum, you also find that the momentum is always having 0 value. Okay, always having 0 value. And this is rather odd, and this is something kind of puzzlement to quantum physicists at the time, okay, because this always averaged to 0, okay. So these are called non-classical states. They're highly spread out and bizarre because they're not localized. You notice that if the probability of finding the particle is proportional to the square of these functions, then the particle is actually been able to be found anywhere within this window. Okay, anywhere between this window, between these 2 points. Okay, people don't like it. So Roy Glauber and Josh Sudarshan found the answer to this problem by looking for the coherent state. Okay, the coherent state, if you were to find the coherent state, it corresponds to a wave packet. So instead of describing by that photon number wave functions that you have, you can actually come up with a wave packet. You can find that this wave packet would actually oscillate back and forth like a classical pendulum. And as you increase the energy of the pendulum, it becomes sharper and sharper. Okay, so another view of coherent light is that the amplitude of the signal is actually uncertain. And because it's uncertain, if you look at the sinusoidal signal, it's not purely sinusoidal anymore. The amplitude is actually has a fuzziness to it, and that's one way to think about it. Okay, and then you can play around with concepts like squeeze light, where you make the probability of the 2 amplitude squeeze in such a way that the noise, if you think of this uncertainty as quantum noise, the noise can actually be reduced at this position. Okay, so let's look more at the coherent state. Okay, and let's look more at the coherent state and find out what it is. So in order to bridge the gap with the classical world, you need the coherent state. And actually, Roy Glauber was awarded the Nobel Prize in 2005 for his work on this area. Okay, so in order to do that, let's rewrite Schrodinger equation in a fashion that I have Schrodinger equation derived or motivated by Schrodinger to be something like this. And this is the eigen equation. Okay. And the first thing that you need to do is to write this equation in a dimensionless form. And the way to do that is to divide this equation by h bar omega naught. Okay, divide this equation by h bar omega naught. And if you do that, this has the dimension of energy, this has the dimension of energy. And you can show that if this becomes dimensionless, you can also move this to become dimensionless. Say if I were to rewrite this equation, it will be h bar 2n 1 over h bar omega naught. Sorry, there's a plus here. Okay, sine nx. Okay, and then this term will become something like that. And then if I define a new variable, because c is equal to m omega naught over h bar x. Okay, if I define then I can actually see that d dx squared is the same as I can write this as by a simple trick. Okay, I can write this like this and then put a m omega naught over h bar out there. It's the same thing. Can you see that it's the same thing? Put a d here. I put a d here. I put a constant in there, but this constant can be taken out to cancel that constant. Okay. And because of that, I can write this as m omega naught h bar d because c. So this is my new variable. Sorry, there should be a square here. Okay. So if I do that, then what I have then is that this constant out front, you notice it's just becoming h bar over 2m omega naught. And it will precisely cancel this constant. So if I write this equation this way, then this becomes half d square d zeta square psi n zeta. Okay, so it becomes dimensionless. I can do the same thing to the second term as well. It would become half cos c square. Let me write it properly. I wouldn't go through the detail, but I could use the same trick by using this change of variable. Then the second term would just become that. Okay. And then I would have a new Schrodinger equation, which is written in terms of dimensionless quantities, which is that half minus d zeta square plus, not zeta, actually it's cos c square, sine of n of cos c is equal to En over h bar omega naught sine n of cos c. Okay, so I have this new Schrodinger equation, and I like to mention that these ENs have been found in closed form. Okay, these ENs of this eigenvalue problem that we have has been found in closed form using classical theory of ordinary differential equation. These differential equations are solvable in closed form. And you can find this En in closed form is given by that value over there. Okay, so what you finally have then is that I can write this equation that I finally have here. Being equal to n plus half psi n zeta. Okay, so this is the simplified version of the equation, and I'm going to start here in the next lecture and continue with the quantum theory of light. The important thing is that you need to find the coherent state. In order to find the coherent state, you need to solve this Schrodinger equation in normalized coordinates. And you need to find what we call the annihilation and the creation operator, or the racing operators. And then with that, we can construct the coherent state. And when you construct the coherent state, you find the coherent state has a property of a classical pendulum. That is, the higher the energy of the coherent state, the more it looks like a classical pendulum. You can use the coherent state to bridge the gap between the quantum theory of a pendulum and the classical theory of a pendulum. And since we are going to describe all oscillations with the pendulum theory, okay, all oscillations can be described by a pendulum. In the case of classical light, we use the classical pendulum, but if this becomes a quantum theory of light, we have to replace this classical pendulum with a quantum pendulum. A quantum pendulum will have uncertainty in its position, okay, like this thing over here. And we're going to talk about that more next time. I will stop here unless you have any questions. Are there any questions? If not, then we'll stop here and we continue next time. And Dr. Na is going to give an office hour tonight, and I'll give one tomorrow night. Okay. Bye-bye. If you know message as you tomorrow night.